Okay, I think we're good. So last time we started talking about functions again, so we are in the handout for 1.4. On the second page, we already spoke about evaluating functions, which has to do with on the functions on the quiz today. Oh, before I forget, our first test is actually next week. It will be about 1 hour to 1 hour and 15 minutes long. Beginning of class. The review for the test is posted. You can get started on that in the recitation session, but you'll have to finish on your own, I think. So, yeah, test review. So if you go to our Blackboard, the Blackboard for our class, the LMSA Blackboard, go to course documents, which is where all the syllabus and all that stuff is. You'll see a folder called test reviews, and there's the test 1 review. And it has instructions as well as things that you should be practicing. It's very important that you follow the instructions and kind of do them how it's supposed to be done, which is another reason why it might be nice to actually do that in the recitation session today. So basically, I link you to the final exams that are on the Blackboard All website, and I tell you which problems to do from those exams, and I give you a time limit in which to do them, and I expect you to like sit down and work on them by yourself with your time limit. So you can probably do some of those in the recitation session today. So so you'll have problem sets from final exams A, B, C, all the way down to F. I would recommend that you leave F alone, if possible, and just do A through E, and kind of only do F if you need extra practice. So if by the time you get to final exam E, you're not getting the grade you want when doing the test, then probably try final exam F, and maybe C tutoring as well. But I would save that for maybe the end of the semester when you're reviewing for the final. Leave final exam F to do it in its entirety. And I'll probably have some other finals as well for you to do it in their entirety and have some mock finals. Is what I'm doing. I think that's it. So yeah, quizzes to get back during the break. We will continue with our material on functions. Test 1 is in the week. The reviews are here. I would get started in the recitation session, and I'll talk to your recitation about that. So we're going to continue with 1.4. So we started talking about functions. I reminded you guys what functions were. We spoke about, what a function is, what its domain, what is its range. We also spoke about ways to represent functions. You can list them as a table of values, a set of coordinates, verbally. You can use mapping diagrams, you can do graphs. So there are many ways to represent functions. And we also spoke about evaluating functions. And this is basically figuring out the output for some given input, which you have to do today on the quiz. So now we are going to move on. Now we're going to write a review for that because you guys are super familiar with functions already. So we're going to move on to the next section, which is talking about combining functions. Again, this is somewhat of a review, so I'm not going to be super comprehensive here, but let's just remind you about combining functions. So we can use arithmetic operations to create new functions from old ones. And so we can, for example, given functions f of x and g of x. So remember, we also described the notation last time. This is just a function who we call f is the name, and we call the generic input x, represents any input variable, and the output is called f of x for that corresponding input. We can make the following functions. We can call f plus g of x, which basically by its definition is going to be you add the formulas for these two functions. You add the two outputs, you've created the output for the f plus g function. There's also a subtraction function. So you can create that function. Basically, the rules, we've spoken about this before, it's you combine like terms. We also described what like terms. So you can create the sum function or the difference function given two functions. We can also multiply two functions. We can have fg of x. And we'll talk about f of g, not to be confused with that. And this is just you're multiplying the outputs. So for this one, you should remember how that would go. You'd apply distributive law. Expand the brackets or parentheses, and then combine like terms, if any. We can also divide functions. So we can create the function f over g of x, and this is just you're dividing their output values. And this is, of course, for g of x not equal to 0. And this one, again, well, pretty much you just divide. I'll be careful when simplifying. You should note that simplifying does not fix or change the domain. And so that's important. That's a mistake that's often made. Sometimes students think when they simplify a function, it means that the things they have to worry about in the beginning, they don't have to worry about anymore. This is not true. So for example, if you're given a function which is x squared minus 4 over x minus 2, then notice that x equals 2 is not in the domain of the function. Then if you simplify, which here you can factor the top. And factor that. Cancel this. You can get f equals x plus 2. You should be aware you still cannot let x equals 2. Right? The fact that you simplify doesn't fix that. Right? This is still going to be a function such that x is not equal to 2, because it was the original definition couldn't fit 2. So while it simplifies to x plus 2, you have to realize there's really going to be a hole there at 2. You can't actually fix something by simplifying it on paper. Right? So be careful with that. So you can divide things. Sometimes they can simplify, sometimes they might not. But just be careful when simplifying. Just note, anything you cancel out is still a factor, even though you can't see it on the paper. Right? The original function really tells you what works from what doesn't. There are cases where we'll need to simplify the functions to make solving certain problems easier, but it doesn't fix the fact that the original problem had a problem. Yes?
So when you're writing the answer, like the answer, you have to include like x cannot equal 0 in your answer? Or is it just x plus 2? Like how does that?
Well, it depends on the context, but you definitely should know that this is not a factor. So for example, one kind of problem could be asking you to find, okay, so they could describe the top as f, the bottom as g, right? And they can say, find f divided by g, which would be this, right? And one of the answer choices might be this, and it might be the correct one. However, if there's a follow-up question like, what is the domain of f divided by g? You have to remember, oh, in the original one, 2 is not included, therefore in the simplified version, 2 still not be included. So in this case, if I were to say, even though on paper it looks like a polynomial, I would say here the domain is actually just everything except 2. You still cannot include 2. And I know that because it came from this. Right? So you should just know, like if you need to talk about domains and things like that, you have to remember the original definition is the most important one. Okay. We simplify to make our computations easier, but the function doesn't care about making our life easier. Okay, so we can actually create new functions from old ones via operations like that. And it's just by combining like terms and all that stuff. Let's actually do some examples here to make sure we understand what that means. Even though I suspect we do, but let's do it anyway. So let f of x equals x squared plus 5x plus 6. G of x equals x squared minus 4. Find f plus g of x, f minus g of x, f times g of x, f divided by g of x. Go. We have f plus g of x. Just remember that that is notation for f of x plus g of x. This means I would take the f of x plus the g of x. What does that combine to? What is that?
Squared plus 5x plus 2.
Combine like terms. There are 2x squares, 1x squared plus 1x squared, 5x, there's no other x. There's a plus 6 constant and negative 4 constant, combine those, so that would be that. If you have these f minus g, just remember this is f of x minus g of x. This is going to be x squared plus 5x plus 6 minus x squared minus 4. Especially here, it is especially important that you do not forget the parentheses. Distributive law will take effect to change all the signs here. S squared plus 5x plus 6 minus x squared plus 4. And so that would become what? 5x plus 10. And that is the f minus g. You go to the multiplication, fg of x, this is going to be x squared plus 5x plus 6 times x squared minus 4. How do you compute what that is?
So 4.
Well, it's not 4 with this size, but okay, how would you do it?
X
To the fourth?
minus 4x squared plus 5x cubed minus 20 plus 6x squared minus 24.
So remember how we multiply out? You take each term in one set of parentheses, multiply every term in the other set. So x squared times x squared gives me x to the fourth. X squared times that gives me minus 4x squared, so that's the first part. And then we went 5x times this, 5x times that, that's the second part. and then we went 6 times this, 6 times that, and that's the third part. Take each individual in one set of parentheses and multiply everyone in the other set of parentheses. Just do it one at a time. Start with this guy, multiply everyone over there. This guy, multiply everyone over there. This guy, multiply everyone over there, and then you combine like terms at the end. So here we have an x to the fourth. There's no other x to the fourth. Remember, like terms are just guys that are the same in the variable part, but the coefficients might be different. Here, there's only one x to the fourth. Look at x squared. We have 2 of them. We have a minus 4x squared and a plus 6x squared, so that's going to be a plus 2x squared. Look at x cubed. There's only one, 5x cubed. So we go with those guys. Then we look at 20x. This is the only one, minus 20x. That's gone, and then the constant 24 minus 24 is the only thing. So that would be the multiplication. Look at d. You look at f over g of x. This just means you take f of x divided by g of x. This would mean you take x squared plus 5x plus 6 over x squared minus 4. And that could be your answer. You might want to simplify to say, does that factor the top? X plus 3, x plus 2, and this would be x minus 2, x plus 2. These would cancel, and so you would have here x plus 3 over x minus 2, and that could be your answer, but again, you have to realize your x cannot be negative 2. Even though there seems to be nothing here suggesting that, you have to remember you cancel the part of it, where negative 2 would be a problem, it will still be a problem, even in the simplified version. There will be a hole at this point. Another important function operation we need to make sure we remember how to do is composition. Right, this is referred to as plugging functions into other functions.
Wait, so with the domain with the x minus 2 at the bottom, it's saying that's always going to be not equal to all the denominators.
Yes, the domain cannot include 2 or negative 2. So here you can see that the domain cannot include minus 2, it cannot include 2, right? Now if you look at this function, you might just think 2 is the only problem, but you just have to remember it was simplified from that. The domain is the same. Right? There's a difference between this was given to you originally versus you were given something else but you simplified it to that. Right? The problems here are still here, even though you might not see them at the time. So composition refers to plugging functions into other functions, right? Functions of functions, we call these compositions of functions. The point is to cut out intermediate functions to hopefully simplify definitions. So the notation is f of g of x. So you see that notation, they'll deliberately put a circle that's not shaded in between two functions, and that would mean the composition of functions. And that is defined, so I'm telling you defining what this notation means, as having f and you want to evaluate it at the output of g. In other words, the function g will do something and give you an output, and then you're going to take that output and use that as the input in the f. So, in other words, you can have the domain of G, right? So you're plugging some x into G. G is going to do something to that, bring it to its range, and it's going to output G of x. But it turns out its range is going to be the domain of some other function f, and that function f is going to take that and move it somewhere else. And it's going to move it to f of G of x. Right? So G will do one thing, right? Give it an input, it will give you some output, and then f is going to take that guy and move it somewhere else. And how you can imagine the composition is it cuts out the middleman. The composition is the function that will start all the way from here and go all the way there, cutting out all intermediate steps. Just think of it as one streamlined function. That guy is going to be your f of G. And so when you start composing things, this is essentially what you're doing. So you can talk about, you can keep bringing the chain. Sometimes you just have to have functions where you know one function deals with certain situations and then other functions have to take over. So you can have, say, a bunch of things, like 4 things. And one function can do this, call that the first function. The next function takes that and does something else. The next function takes that and does something else. So you have these bunch of functions just passing the buck. If you want to simplify the process and talk about one big function to go all the way from the start all the way to the end, well, that's just a composition function. And his formula might be a simplified version of all the mess that's going on in the middle. Right? So there are times when you have that situation. Right? Functions only deal with their small sphere, but they are interconnected. The composition streamlines this connection. Yes?
So if you have an f of x, you're plugging in g of x or all of f's x values, right?
Right.
Okay.
So we're going to do some examples where this means, right? So the idea is the following, right? We have a bunch of functions that are interconnected. We want to cut out all the middle pieces and talk about how do you get from here to here, right? Whenever that's the idea, you would create a composition of functions. Now, algebraically, to actually mathematically work one of these out, this is how you want to think of it, right? The guy that's on the right gets plugged into the guy that's on the left. So you take his outputs as this guy's inputs. And so let's actually, and by how we thought of functions last week, which I reminded you, you want to think of functions as templates, where this is just a void that whatever you fill in here replaces all the x's in the function. So let's do some examples. Suppose f of x is the function 2x squared plus 3x plus 1. G of x is the function 2x plus 1. Find f of g. Find g of f. Find f. So A, f of g means we're going to take f and we're going to plug the g inside of it. Okay? So again, remember how we're thinking of the f here. We're thinking of the f as something like this. And we're thinking of the g as an object like this. They're just, the x's are placeholders. Now in this case, I want this part to be filled in with g, which means I have to put g here, I have to put g here. Everywhere there's an x, I need to replace it with a g. And so what this is, you just start writing out the f, which that's just going to be 2 times something squared plus 3 times something plus 1. And then what is that something? Well, g of x is that something. So everywhere I see x, I'm going to put g in that position. So now g of x is actually this guy. That means I can do that. And now let's actually simplify this. What is that? How do you simplify that?
Just multiply the parentheses, like 2x plus 1 times 2x plus 1.
Okay, what would you get?
Hold on, I didn't make it that far.
4x squared
4x squared
plus 4x
plus 4x
plus 1.
plus 1. Remember the formula, it's a squared plus 2 times this times that plus this squared.
6x.
Right, here you can distribute 6x plus 3. Here there was a 2.
8x squared.
Probably should have emphasized that you need to keep this in parentheses so that that 2 in front distributes. So you'd actually start moving that out. 8x squared plus 8x plus 1 plus 6x plus 3 plus 1. And now you start combining like terms. So there's only one squared term, that's 8x squared.
Isn't it plus 2?
Yeah.
What?
Isn't it 8x plus 2?
Plus 2. So we have one squared term, that's 8x squared. We have two x terms. So we have 8x plus 6x, that's 14x. Then we have just the constant terms, which is 2 plus 3 plus 1, 6. So that's what that would simplify to. G of f. Well, that just means I take g and I put f inside of it. Well, that means I have 2 times something plus 1, and now I know that something is f. So I have 2 times the f, which is 2x squared plus 3x plus 1 plus 1. This one's easier, expanding here. 4x squared plus 6x plus 2 plus 1. And that's just 4x squared, square term, 6x, there's only one x term, and the 2 plus 1 is 3. C. What is f of g of x? Yeah?
Isn't it the same as f?
Yeah, same as a. I just throw that in there to emphasize that these two notations mean the same thing. I get students asking me that from time to time. What does this mean? Well, it means that. Okay, what does this mean? It means that. Right? There's two different notations, they mean exactly the same thing. Okay? So f circle g or f parentheses with g inside, they mean exactly the same thing. G. What does it mean to say f of g of 1? Well, we now know what is f of g of x, right? We found that, well, in part A. So now, f of g of 1 just means evaluate this at x equals 1. That's what that means. So I'm just going to go and replace the x here with 1. Right? So similar to what we're doing with the function definitions. So we are going to get here 8. I'm thinking of this. I'm thinking of the x's again as just some placeholder, and now they want me to put 1 in that place. So it would be 8 plus 14 plus 6, which is 20. Now, I want to mention that there were, in the event that we didn't do all of these, there are a couple ways you could have looked at this. So, another way is to first find the g of 1, right? So we know g of 1 would be, well, it's 2 times blank plus 1. Yes. So then I would plug 1 into the g function, that would be 3. Then find f of the 3. So I know f is just going to be 2 times something squared plus 3 times that something plus 1. So now I can put 3 in here. That'll be 9 times 2 is 18 plus 9 plus 1, and again you get 20. So depending on what you've done before at this point, here what we did was we first found f of g, then evaluated at x equals 1. Another way would be to first find g of 1 and then plug that into f. You will get to the same answer in either case. They are the same thing in fact. Because again, when someone writes f of g of 1, they're still saying f of g of 1. So you could actually just find g of 1 and plug inside. It's the same notation. Which means there are a couple ways you can do it. Do whichever way you prefer.
Right, you
Yeah.
asked me with the 8x, the 8x squared one? Did you just make those numbers up, or did you?
No, we computed this earlier in
Oh,
part
okay.
A. In part A, it was here, I erased it, it was
Okay.
8x squared plus 14x plus 6. So we actually found that first.
Okay.
Then we plugged in 1. Right? The alternative would be to find the g of 1 and then plug that into f. You would ultimately get the same answer. But... So yeah, the numbers aren't random. We actually just computed that earlier. So that's how you would mechanically deal with function compositions. There's a very important kind of composition, and we are going to see in a couple weeks. Why this is so important. It is called the difference quotient. Which again, you guys have seen many times before. You've even seen it in this class, put it on a couple quizzes already. So if any of you have experience with calculus, you'll realize why this is important. For those of you who haven't, you'll realize that, man, they've been bothering me about this guy since algebra and pre-calc. What's the big deal? We're going to see what's the big deal eventually. But it's the following definition, which you should have memorized. Given f of x, its difference quotient is the formula f of x plus h minus f of x over h. Or, there are a couple ways to write this down. F of b minus f of a over b minus a. And so those are two formulas. This one is usually used, we'll talk about this later. Typically used when discussing average rate of change. We're going to talk about a concept called average rate of change. And this formula is just a little bit nicer to use in that context, but this is typically used otherwise. Right. So they're essentially the same formula, and when we revisit this, I'm going to explain to you why they're essentially saying the same thing. But you should know both formulas at this point. So if I ask you to compute the difference quotient, I give you a function. Here's a function, find its difference quotient. You should know that you should be computing one of these two things. And in the event that on like a final or something, there's a multiple choice, you'll know which formula they expect you to use based on what variables. So if you see there's an H in the answer choices, you should be using this one. If you see A's and B's in the answer choices, you should be using this one. Right? So the note, but these are the very typical notations for the difference quotient. So as you see, it's just a combination of composite functions in the sense here, it's like you took the function x plus h and plugged into f, and then you create this whole formula around it. I think we can actually just jump into some examples here. Because again, this should be somewhat familiar, but I want to make sure that you realize your algebra skills are on point. You should be able to compute things like this relatively quickly. So let's just use some more examples here. Find the difference quotient. So I gave you a function f of x equals x squared, find its difference quotient. F of x equals square root of x, find its difference quotient. F of x equals 1 over x, find the difference quotient. There are a few terms here. Find the difference quotient. Find the difference quotient. So sometimes they'll actually give you this formula in a problem, but sometimes they won't even tell you the formula. They'll say the phrase difference quotient, and they'll expect you to know the formula. So these are things you have to memorize. FYI. Alright, so the phrase the difference quotient should bring up these formulas into mind. So you won't always be given the formulas. I can't guarantee that you'll get them. So, assuming we have them, so f of x equals x squared, what would the difference quotient look like here? Let's say I'm computing this one. What would that look like? How would that look?
F of x plus h squared minus
F of x plus h squared. Like that? What? Like what?
x plus h squared. Like parentheses.
Parentheses? Okay.
Minus x squared over h.
Just take a second here. Common mistake. Don't do it. Is to write x squared plus h and minus x squared all over h. This is incorrect. f of x plus h doesn't mean you just take the function and add an h to it. F of x plus h means everywhere you see an x, you replace it with x plus h. Remember how to think of functions. It's very common for students to just copy down the function and then put a plus h at the end. Very wrong. Okay, this is the right way to do it. Continue. How do you finish up? Huh? Well, that would just be x squared plus h squared, right? Another common mistake. What is it?
X squared plus 2xh
H. Mention a common mistake. Make sure you don't do this. Or if you even thought about it, go home, think about what you did, make sure you see why you thought about it and correct the mistake in your head. Okay. So that would be wrong to write that. If I had a dime for every time students make one of these mistakes, boy. Okay, but assuming we don't fall for those mistakes, what'll happen next?
x squared.
Well, the x squares will die. We have x squared minus x squared. And so we'll have 2xh plus h squared over h. You can cancel this, right?
No, you have to take out the
No.
h.
Another common mistake. Cannot cancel. Can't cancel across sums. So don't do it. Okay. How do we move on from here?
Take out h.
H is a common term in the top.
Cancel it.
Now we can cancel because of the multiplication separating the two things. So 2x plus h is the answer here. Questions on that? Now, if you don't normally make these mistakes, don't write this down, but if you realize you thought it, but you just didn't say it, make sure you write it down. Like, I cannot. That's illegal for me to think that. Freedom of speech here. Okay. What about for the square root of x? If I want to compute f of x plus h minus f of x all over h, how would that look?
Square root of x plus h.
Right, so we have the square root with x plus h underneath it. Right? So if you don't write this, if you write that, it's wrong. You have to write that. Right? The x plus h must replace the x. The entire thing must be under the right one. It's very important that you're sure to extend this to cover the h. Right? Minus the function x squared all over h. How do you simplify that?
Conjugate it.
Conjugate. How? What is all about?
Square root of x plus h.
Multiply and divide by the conjugate. That's what this guy's called. This is called the conjugate. We multiply and divide by it, so we're multiplying by 1. So it's not changing the value. The reason why we multiply by that is because now, if we look at what the numerator looks like, it looks like a minus b times a plus b. This means we know the answer should be a squared minus b squared. It's difference of squares formula, which means the numerator will simplify to this squared, which is just going to be x plus h, minus this squared, which is going to be x. in the denominator, we'll just multiply these guys across. That looks like it's not plus x. Another rookie mistake, let me mention it here. Do not expand the denominator. Never expand the denominator. You always want your denominator in a factored form. If you can factor the denominator further, do that. Never expand it. You want the parentheses there. You want the factors there. Why? Because you can only cancel across multiplication, so if there's something that should cancel, you want your denominator to be able to do that. So you keep it in the most efficient form to be able to do that. Now what happens? X minus x. So we'll be left with h over now what?
Wait, why did you cancel out the x's?
Because we subtracted them. X minus x.
Oh,
So it's a subtraction, not a cancel. And now we can cancel because there's multiplication here, so we can cancel the h's. Remember on top, there'll be a 1 left over. And that would be the answer. Yes?
So if you do cancel the x on that one, wouldn't just that h be left over, so can't you cancel or no?
Yeah, I wrote that here.
Oh, okay.
So the
Sorry.
h is left
You're
over.
going so fast, sorry, I can't do
Yeah. Oh, yeah, we did that.
Okay.
Something to mention here, and to simplify the difference quotient, just to make sure that we're all aware of how do you know when to stop, where at what point do you consider it simplified? To simplify a difference quotient, requires canceling the original denominator. So if you have f of x plus h minus f of x over h, keep going until you cancel the h. If you do not cancel the h, it is not considered simplified. We'll see why later, but just know now, once you start plugging functions here and you're doing your algebra and you're simplifying stuff, you need to cancel that h. Here, I cancel the h in the denominator, and now I'm okay, right? If I stopped at any point before this, it's not simplified. If you have f of b minus f of a over b minus a, you need to keep going until you cancel the b minus a factor in the denominator. So it's very important in the difference quotient when you're simplifying it, you keep going until the original denominator gets canceled. What about that one? What would that look like? Huh? 1 over x plus h? Minus 1 over x?
x plus h, 1 divided by
Right. Right. I just made the common mistake. That is not correct. It makes all the difference in the world. Really, if you do that mistake where you just copy the function and add an h to the end, it's always going to simplify to 1. So normally when I ask a problem like this, like on a quiz or something, and I see someone writes 1 as the answer, I know what happened, right? Even though I didn't see the work, they added the h separately instead of replacing the x with x plus h, right? It has to be x plus h in the denominator, not 1 over x plus an h beside it. Okay, so that's the correct first step. That becomes, very important you think of functions that way. I'm not exactly sure why, but it's very common for people to think of it the other way, thinking of adding an h separate. Just have it in your mind, that's not how you want to think about it. The x plus h replaces the x. How do we simplify that? Yeah?
Can I?
No, how do you know it's wrong? What were you gonna say?
The
LCD,
LCD that you
right? Yeah? What would be the LCD here? Right, it's just the multiplication. So first, this is a complex fraction, you have fraction inside a fraction. The first thing you're gonna wanna think about is what's the LCD? In this case, it's x times x plus h. Now, knowing that, what do? Right, you multiply and divide by the LCD. That's how you simplify a complex fraction. Well, there are other ways, but this is pretty much the fastest way I found. So again, you're multiplying by 1, right? Because you're multiplying by something divided by itself, but at the same time, it will simplify matters greatly. So what's going to happen is you're going to take this guy, and you're going to multiply that and multiply that, because the distributive law is going to take it. Now, what's going to happen is if I take this and multiply that, put it on top, you'll realize the x plus h's will cancel. And I'd only be left with an x. Minus, if I take this, multiply that, the x's will cancel because this is now on top, and I'd be left with the x plus h. It is very important that you realize that there should be parentheses here. Another common rookie mistake is to forget the parentheses there. Divided by hx, x plus h. Never expand the denominator. Right? Just move it beside it. Don't start multiplying out. So I'm just showing you some common things here, some common algebra tricks. So you should remember how to expand the binomial, how to conjugate something, how to simplify a complex fraction by multiplying and dividing by the LCD. These are all skills you'll need to be able to master and be able to use whenever appropriate at a moment's notice. Now here, x minus x, and so we would have a negative h left over in the top because of the distributive law. Negative sign would multiply h. Now the h's would cancel because we have a multiplication of all terms here. Minus 1 over x times x plus h. And that is the simplified version. Because I've canceled the original denominator. This h is fine, he wasn't there originally. Cancel the original. Since on that one. Good. Now the last two we're just using familiar techniques, but making it slightly more complicated. It's very rare for someone to ask you to do one on one of these simple functions. You usually have several terms to do. Well, in the previous line we had negative sign distributes, which is why the parentheses is important. this one look like? Yeah?
1 plus x plus h minus 2x plus 2 parentheses x plus h squared over.
Literally, remember? F of x plus h means, go to the original formula, every spot in which you see an x, open parentheses and put x plus h.
Over h.
Okay, so now we have the minus
Minus,
1 plus x minus 2x squared, that's the minus f of x. Parentheses is important, put that in red. So that's something you should pay attention to, and pay attention to the fact that I replaced all the x's with x plus h. See how many times I repeat this? Someone's gonna, on the test, they're not gonna do it. Happens all the time. Pay attention. Very, very important.
over.
All over h. Okay, now what? Well, we can start removing these parentheses, so hopefully we can simplify something to eliminate things. So we have the 1 here, that just distributes to x plus h.
Minus.
This guy, minus 2 times x squared plus 2xh plus h squared. Parentheses should be here. We'll forget that.
Minus 1
No, I can distribute this, minus 1 minus x plus 2x squared
over
over h. Distribute this one. All over h. We're not done because the h is still in the denominator. You keep going until you cancel it. Now what do we see?
Now you
Huh?
combine like terms.
Combine like terms, so what will happen?
So you cancel the 1 and 1.
Yeah, so we have 1 minus 1
Negative x and x.
plus x minus x
2x squared minus x. 2.
minus 2x squared plus 2x squared.
I don't see it.
That's it. So we're left over then h minus 4xh
Minus 2h squared.
minus 2h squared all over h. So that takes care of those three. So now we can cancel the h here?
No.
No, we cannot cancel across sums. So what do we do?
You take out the h.
Factor it out.
Cancel.
Now we can cancel because there is a multiplication. So it's 1 minus 4x minus 2h, and that is the answer. Because we've canceled the original denominator, so I know I can stop now. That's good enough. Let's do the last one. Now this one, you'll notice something. You'll notice that when we had something like 2x, it'll kind of be like this where we're just expanding parentheses in the top and eliminating stuff. We did the 1 over x, and that required a different technique, right? That required a multiplication and division by the LCD. So here we have 2 different types of functions that would require 2 different algebraic techniques to simplify. Now, every now and then something like that shows up, right? The technique would vary between the 2 parts. Now, what you need to do here is to remember that you can always split a fraction across the numerator, Right? You can't do it across the denominator, but you can do that across the numerator. And so the idea is, whenever you're given something like that, you're going to want to separate these two sets of fractions and do one technique on one at a time. And it'll make your life a lot easier than trying to do everything all at once. So let's see how that would look here. So again, what f of x plus h means, go to the original function. In every spot that I see an x, I am going to replace it with x plus h. So I have 2x, replace that with x plus h, plus 1 over x, replace that with x plus h, minus, parentheses, write the original. Now, I immediately notice that these two guys here are fractions. The best way to simplify those would be to multiply and divide by the LCD. Whereas these guys here will kind of just deal with those by expanding parentheses. So what you can do is just separate the two. And put each part over x. Right? So put all the fractions on one side over x, put all the guys that are not fractions on the other side over x. Now individually, you'll do a different thing. So for the first one, that's not going to be bad, it's just distributive law. That'll be 2x plus 2h minus 2x over h. This and that will die, and the h's will cancel, and you will just get 2 on this side. Plus, now for this one you realize you are going to multiply it by x times x plus h over x times x plus h. So here the x plus h's will cancel, you get an x minus parentheses. Here the x's will cancel, you get an x plus h over h x plus h. We have x minus x. So we have a minus h over h x plus h. Cancel the h. And so we end up with 2 minus 1 over x times x plus h. So you're asked to find the difference quotient of some combination of terms where you need a different technique for each kind of term. It's fine, just split them up. You can actually do that. Do whatever technique you need over here, do another technique over here, and just add them together at the end. And that'll be fine. Some more on domains. So we sort of discussed this before, but let's look at it again. And just hammer home some of the things I was mentioning earlier about how simplifying doesn't fix your domain. So domains, what you can think of this as is the set of inputs that work. I.e. makes a function defined. I.e. makes the output a meaningful answer. So all the things I can plug into a function where the output will give us meaning and it'll have meaning for us, we call this set of x's the domain, which should be important domains can be given by some restriction. Or implied. Rather, those we covered a couple classes ago. A few, I don't remember. It was exactly a couple. So we looked at domains of like the square roots. You know that if it's an even root, what's underneath it needs to be 0 or bigger. If there's a fraction, denominator can't be 0, things of that sort. So those are some rules where if you're not given a restriction, you follow those rules, we'll call it implied, but sometimes you're given a restriction. So if you're given like f is equal to 2x plus 1, this is a polynomial, you know that the domain of f is, well, all real numbers, you can plug anything in there. This guy will be called the implied domain. And if there's no other information given to you, you will consider that as the domain. Versus, someone tells you, okay, here's f of x equals 2x plus 1. We're only considering x between 1 of less than 5. Right? So they tell you, this is the definition, that's where the definition works. Turns out that the domain here is going to be that guy, 1 to 5. Now, yes, we know it's a polynomial. Technically, you can plug in anything you want, but this was given. It's a restriction that they are giving to you. You must obey given restrictions. If no restriction is given, then yeah, just indiscriminately plug in any x you can get away with. With a polynomial, you can get away with anything. So sometimes a problem will tell you a domain. Sometimes the domain changes, like based on piecewise functions. Right? So sometimes they'll tell you it's 2x plus 1 in this region, but it's something else in another region. So you just know for the different inputs, you'll plug it in to different points in the function. The range is just a set of corresponding outputs. So once you figure out all the things you can plug into your function, now you look at what do they evaluate to. Look at all the set of those things, that's called the range of the function. To do is find the domains and ranges of the following. So we'll do this, and I'll show you a little quick and easy thing on the calculator, and then we'll take a break. And that'll end the section. So what about A? What is the domain of F? Domain. What is the domain of F?
-32.
negative infinity to infinity. These are all the x values that we can plug in, and it will give us a meaningful answer. This is why? Because it's a polynomial, and we know polynomials works everywhere. What is the range of f? Now this might be, what is the range of this function? So remember what the range is, it's the set of corresponding outputs, corresponding y values. How do you think you'd figure that out?
Solve
Yeah.
for like x, get like the two values maybe. You know, like x plus 3 and x.
What's it
Okay.
plus 0?
X plus 3, x plus 2. Okay, and then what?
I don't know, we'll guess.
We're going to deal with quadratics right after this, but let's see, just to jog your memory. One thing you could do is using those. You should know how to sketch it by using those. What would the sketch look like? Huh? If you factor it, what do you do with those guys?
So it's negative 3 and 0.
Right, you would set this equal to 0. You think of x is negative 3 and x is negative 2. That actually tells you where they touch the x-axis. So you would have a graph that looks like this, right? Where this is, well, not drawn to scale, obviously, negative 3 and negative 2, right? So now remember what the range is. It's the set of corresponding y values. So our range will be the guys from here going up. That's going to describe the range. Now, how can you find that set of those set of values?
Can you take like the x point and plug it in to find y?
What point?
Like negative 3, let's say, or no?
Well, negative 3, we know the y is going to be 0.
Okay, so then,
This point seems to be the important one here, the lowest point. How do you find that?
Get
What's it called? Remember what
the
it's called?
vertex.
This is called a vertex. Okay, so how do we find the vertex?
So it's negative. What I would do is I would just get the y from the vertex formula. And with the
Yeah, but what is-
formula,
Isn't it
negative.
it was like 2a over something b, right? I think.
H comma.
I don't remember.
X equals minus b over 2a.
There you go.
Okay, that's how you find the input
B
for
squared.
the vertex. So in this case, your b is 5, your a is 1, your b is 5, your c is 6. So a is 1 and b is 5. So this will be minus 5 over 2. Right now that will be the x value for the vertex. Now remember what the range is. The range is a set of y values. So given that I found that doesn't really, it doesn't end there. I'm going to have to figure out what is the y at this point. Okay? So the y will be,
I'll just plug it in.
well, you just plug it in. So it's minus 5 over 2 squared plus 5 times minus 5 over 2 plus 6. So this is 25 over 4 minus 25 over 2 plus 6. So that's what minus 25 over 2 plus 6. 6 would be 12 over 2. So what is that? Minus 13 over 2? Is that right? So this goes from minus 30 over what?
Oh, I was gonna say that y such that y is greater than or equal to
Right.
negative 13 over 2.
And it can go as big as it wants. So that's how you find the range of that function. It's a quadratic, so they're very it's very typical for you to find the range of these guys by just finding the vertex. So that deals with that. Right? What about the x squared minus 4? What's the domain?
Or no, positive two.
What kind of function is it? It's a polynomial. So what is the domain?
Negative
Everything. Okay, let's talk about the range. Now, this one we should be able to graph quickly via transformations. That just like you take the x squared graph, you shift it down 4 units. What's the range?
Y such that y.
Anything that's 4 or bigger. So it's C. So C was F divided by G. What does that guy look like? Well, it was the F, which is x squared plus 5x plus 6, or x squared minus 4. What's the domain?
So x can equal -2 or 2.
So in interval notation, you cannot be 2, -2, you also cannot be 2. So we have that guy. The range we'll do later. It's a bit difficult for a problem like this until we cover some later things. We'll even sort of look at how to graph things like this. But that's probably best left for later, because there are some issues here that we might have to deal with.
So it won't be on the test. So it won't be on the test.
No, the test is only going to have stuff that I never talk about. Like that's entirely what the test is going to be. So all that stuff where I say, yeah, we're not going to do this yet, that's the stuff I'm going to put on the test. That's how math teachers do. Just want to see the world burn. Okay, P, rho x squared, domain. And range. Domain. It's a kind of polynomial. Range.
So 0 to infinity.
0 to infinity. Remember what x squared looks like? Well, you should. It's like that. All the y values are from 0 and bigger. There are no negative y values here. Q equals the square root of x. It's a domain. 0 inclusive to infinity. What is the range of Q?
0.
It's also 0 to infinity, right? Again, you can know that from the graph of the square root, which we've seen a couple times already. So the x values start here and move to the right, the y values start here and move up, so they're both from 0 to infinity. That was E. What about F? So here I'm going to take P of Q of x. We know this means that I'm going to take P, I'm going to plug in Q. So this means I'm going to take something squared, it's going to be a radical of x, and I'll get x. What is the domain? Hmm?
Not sure.
Why are you not sure? Huh?
Would it be a vertical line too?
What vertical line?
I don't
I
know.
don't know.
I'm confused if it's, yeah.
Well, X isn't a vertical line. Are you talking about Y equals X?
Yeah.
Remember that looks like this. So what's the domain? Yeah.
Negative grade class.
No, that's the same as all real numbers. So remember what we said earlier, simplifying does not fix the domain. What is the domain? 0
0,
to infinity. Why is it 0 to infinity?
because based off of what I'm seeing in the square root of x.
Because there was a problem here. We couldn't plug in negative numbers here. Just because I simplify it to look nice doesn't mean suddenly I can plug in negative numbers. Simplifying does not fix the domain. This x isn't a real x. This x is an x that you got by being unable to plug in the negative side. Right? You only have half of this graph. So if you take the square root of x and you square that, it's not everything, because the negative side didn't exist before. You simply squared the right side of something. So that's the domain. Simplifying does not fix the domain. Just because you might simplify something and you see x, oh, that's a polynomial, whatever. No, be careful where you're coming from. And of course, that would mean that the range
Would also be
would be 0 to infinity. Okay, Q of G. So Q was the radical, and G, I believe, was S squared minus 4. How did we do that? Well, we've seen something like that before. Let's see how much you remember. What's the domain of that? Yeah, so how would you do this one? For the domain? Where do radicals work?
Would it be negative infinity, comma, -2 and 2 comma infinity, because you would have to set the thing into like x plus 2x
Well,
minus.
these would be included,
Yeah.
because you can include the 0. Right. So remember, for this radical to work, you need your x squared minus 4 to be greater than or equal to 0. Now you can actually solve that by getting x plus 2, x minus 2 greater than or equal to 0. So you'll get x equals 2 and minus 2, and you can test the intervals, but it's a lot quicker to realize that we know the graph of that, and we know that it's positive here and here. So from 2 to infinity it'll work, and from negative infinity to minus 2 it'll work. So we have that domain. And now clearly you can see what the range is. It's going to be 0 or bigger. let's take a quick look at something you can do on your calculators here. First. Nothing too crazy, I just want to show you that your calculator knows how to find composite functions. So, if you want to actually compute a composite function on your TI-89, this can be done. So the first thing we're going to do is we're going to turn it on. Let's go to the Y window and let's put in our functions. Now these we had from last time. Let's go up, clear this. Let's throw in a few functions. Let's say x squared minus 4. And let this one be x squared. And let this one be the square root of x. So I just entered a few of those functions. So let's actually find some composite functions. Let's say I wanted to find y1 of y2, or I wanted to find, let's say, y2 of y3. There's nothing too crazy here. So if you want to go to the home window, and those are already entered into your y, the nice thing is you can literally just type it out as you kind of would on paper, not with the circle notation, but with the parentheses notation. So you can type y1 of y2 of x. And it will actually give you the composition function. Right? That's like it took the x squared and plugged into the x squared minus 4. The result after simplification is going to be x to the 4th minus 4.
You're on F1,
Huh?
you're on F1.
No, I'm at home. To enter the functions, you mean? To enter the original? You go to the Y window, so you press the green button and Y. And then you enter the functions. So in Y1, I entered x squared minus 4, just a random example. In Y2, I entered x squared. In Y3, I entered radical x. Okay, so let's say I wanted to find y2 of y3 of x. Right, so I believe y3 was the square root. It took it and it plugged it into x squared. Okay, now you should also know that your calculator can evaluate things. So for example, I could ask it, well, what is y1 of y2 of 1? Right? So evaluate the composition function at a specific point, and it'll tell you, oh, it's minus 3. Now let's see if I can trick the calculator here. Right? Our y3 was a radical, right? That's what I entered. So it means that this guy is a radical plugged into a square root. So technically, even though the calculator told me x, this x shouldn't be everything, right? Like a negative x shouldn't work here, right? But let's see if the calculator makes that mistake. Let's say I did y2 of y3 of minus 1. The calculator understands, yeah, I simplified it and gave you x, but you can't plug in anything into that x because simplifying does not fix the domain. So plugging in minus 1 into the function x is going to give you non-real result because technically that x is not an x. it's an x for only half of it. So that's it, we'll take a break. We will come back. But yes, you can just plug in your composition functions into your calculator by just doing the parentheses notation. And you can even evaluate it at certain points. So if you ever need to do that, you can. I'll return the quizzes from last week and then you guys can take a 10-minute break. Or